We now learn about a second randomized rounding algorithm that's a bit more involved because it doesn't just randomly choose variables to be 1 or 0, but it does some pre-processing. And the pre-processing it does is everybody's favorite, an ILP, or the relaxation of an ILP. So for a start, I will ask you, can you write me an ILP for the MaxSat problem? Yeah, let's try to do it together. What are our variables that we must have? We want to have a variable for every input variable that tells us whether it is assigned to a 1 or a 0. And then we also want to have a variable for every clause that tells us if the clause is satisfied or not. What do we want to maximize? We want to maximize the sum of the weight of those clauses that are satisfied. A variable set j is 1 if it's satisfied and 0 if it's not, so we just want to maximize the sum of all the weights multiplied with this variable. So if it's satisfied, it's a 1, its weight gets counted. If it's not satisfied, it's a 0, then it does not get counted. And what are our constraints? We have to make sure that set j is 1 exactly if a clause is satisfied. And to do that, we take a constraint for every clause. And we look at the variables that are in the clause as a positive literal and those that are in it as a negative literal, right? Like we write down here. We have all the positive literals in pj and the negative ones in nj. And now we want to sum up how many literals are correct. So we sum up all the variables that are as a positive literal in it, and we sum up 1 minus all the variables that are in it as a negative literal. So this gives me exactly the sum of the satisfied literals in a clause. And I want to make sure that the set j can be 1 only if this is at least 1. So we just say that this has to be at least as large as set j. And since all these are integers, this is either a 0 if nothing is satisfied, and this tells me set j is also as most 0, or this is an integer at least 1, and then, since we want to maximize, the program will put set j as a 1. And that even means that we can get rid of the integer requirement here. It will always choose either a 0 if it has to, or a 1 since we want to maximize if it can. But still, this is an ILP, so we have to compute its relaxation. And the relaxation, here we only have to change the variables yi to also be somewhere between 0 and 1. And that we can solve optimally. So we optimally solve the LP relaxation of our problem. That gives us some assignments for the variables that maximizes the sum of the satisfied clauses. But the problem is, of course, those variables can be assigned fractionally, so it's not really a valid solution. And what we then often do is that we round the variables. So for example, what we did before was we said, yeah, we take all the variables that are at least assigned with 1/2 and we round them up. Or here what we could do is we take all the variables that are at least 1 divided by something and round them up. Maybe the length of the longest clause, and then we get something. But we want to do it a bit differently. We want to randomize the rounding. And we want to randomize it depending on the assignment of the LP relaxation. So let's say we have an optimal solution for it. And y star are the assignments for the variables, z star for the clause variables. And now we want to set every input variable of our MaxSat problem independently to 1 with probability the assignment of the LP relaxation. So if the LP relaxation assigns a variable to 1, then it will definitely be a 1 here. If it assigns it as 0, then it will definitely be a 0 here. If it assigns it as 0.5, then it's a 50% chance that it's true or false. And if it's a 0.9, then there's a 90% chance that it's true and 10% that it's false. And if we do this, then of course we get a valid solution, and the approximation factor we get is 1 minus 1 over e, which is about 0.63. So this is slightly better than the algorithm that we had before, where we only got 0.5. And in the next part, we want to prove that this approximation factor holds.